Hello and welcome to our lesson on applications of linear systems. So applications means we're going to be applying the process of solving linear systems. The process is we've learned graphing, substitution, and elimination. We're going to be applying those solving processes to new situations. In essence, means we're dealing with some word problems where these skills are useful. The tough thing about word problems is there isn't one way to solve them all, but there is a general strategy we've discussed before, and let's recap that again. Okay, the first thing we want to do when we're dealing with a word problem is we want to read it. And again, that seems kind of silly, but sometimes we're so eager to work that we just try to start writing things down without fully understanding or reading the problem. So let's read it maybe even a couple times. And, if you want to, you can mark the text along the way, highlight, underline important information. But after you've read the problem, use what it's asking you to find to define your variable. And in this case, we're defining variables because we're looking at a system. Okay, so define the variables. What is it in the problem? What are the two things that we are looking for the values of? And then we're going to try to write a system that models that problem, models the information that we're given. And that's the hard part, because we can write any system we want and solve it. If we have written the incorrect system, it doesn't matter if we solve correctly. So we have to be really careful with that step. Then we're going to solve using one of the processes that we've learned. Matrices, yeah, that shouldn't be in there. We haven't learned matrices. When you move on to college algebra, that may be something that you see. We're going to solve using one of the options we've learned. I would say graphing with Desmos is probably the easiest, so that's what I'm going to lean on here. And the last thing is, because we're putting context into this, we want to make sure we have an answer that makes sense to that problem and that we've answered the question in a way that makes sense. Okay? So I've got some examples here for you. Let's try to work our way through some of these and apply the solving systems processes we've been talking about. So number one says Tyrell bought 4 pens and 5 pencils for $6.71. Dana bought 5 pens and 3 pencils for $7.12. Find the cost for 1 pen, 1 pencil. So we're looking for the cost of a pen. Let's call it X. We're looking for the cost of a pencil. Let's call it Y. Those are our two variables in this situation. Now, what are they telling us about here? The two things they're telling us about, the two people they're telling us about here are Tyrell and Dana. So let's write one equation for Tyrell. What do we know about Tyrell? Well, he bought 4 pens. That would be 4 X's. And, let's put a plus sign for that, he bought 5 pencils, that's 5 Y's, for a total of, so let's put an equal sign, $6.71. Okay, and then Dana, what do we know about Dana? Well, she bought 5 pens, that would be 5 X's, and that's a plus, 3 pencils, that's 3 Y's, for a total of, that's an equal sign, $7.12. And there we have a system. And solving using elimination would be the best option there if you're doing that algebraically. But again, I'm going to lean on my calculator here. I mean, it's hard enough, it's going to be hard enough for us to set up some of these word problems, so let's not try to stress about the solving. So 4x plus 5y equals 671, and 5x plus 3y equals $7.12. Our solution, the point where these two lines are crossing, is 119. Solution at 119 and 0.39. And remember, x's were pens, and then y's were pencils. So what does this mean? It means 1 pen, 1 X cost $1.19, and 1 Y, 1 pencil cost 39 cents. So pens are $1.19. Pencils are 39 cents. And there we have it. Okay, not too terrible for our first problem. And that's just getting us warmed up here, I hope. Okay, let's look at number 2. Number 2 says, suppose you have a piggy bank full of dimes and nickels. there are 140 coins totaling $11.30. How many dimes are there? So it's only asking us for the number of dimes. Let's go ahead and call that D, but we also don't know how many nickels there are. So let's call the number of dimes D, and let's call the number of nickels N. Okay, in this case, our two equations, again, have to deal with the two bits of information that we're given. So first, we're told that there are 140 coins. So one equation we're going to write is for the number of coins. It says that there are 140 total. That means the number of dimes plus the number of nickels has to be 140. Now the second piece of information they're giving us is about the total value. So we're going to make a second equation for the value. We know that it's 10 cents for every dime plus, that was a 0, plus it's 5 cents for every nickel, and all together that's going to total $11.30. Okay, so we have to use the information that we're given in order to write our system. So now we just need to find the solution, and again we're going to do this with our calculator. Now I called the variables D and N there, but I'm going to go ahead and use X and Y because Desmos recognizes those variables. 10 cents for every one of those, and 5 cents. Oops, got an extra decimal in there. Plus, come on, fingers. 5 cents there, and then 11.30. And we're going to have to zoom out a little bit. That 140 is kind of a big number, so there it is, 86,54. So we have a solution at 86,54, and the first variable was D. That's normally an X, right? And then here was N, and so we have 86 dimes, 54 nickels. Okay. Now I didn't check the last one, but I suppose I should, and I want to reinforce that you should be making sure that your answers make sense. If you add 86 dimes and 54 nickels, that's 140 coins. 86 dimes at 10 cents a pop, and 54 nickels at 5 cents a pop does total $11.30. Okay, so you can check your work to make sure it makes sense for your problem. All right, next. At Barrows, a large pizza costs $10 plus $1.25 per topping. At Brothers, a large pizza costs $8.75 plus $1.50 per topping. This one says to write and solve a system for the scenario and interpret the meaning of the solution. So here, our two variables are kind of interesting. It says at Barrows, a large pizza costs $10 plus $1.25 per topping, right? The two variables here are what is the total cost going to be for your large pizza, and that's based on how many toppings you put on that pizza. And this linear system is going to look familiar. It's going to connect back to what we were doing in Module 3. So first, they're telling us about Barrows, and let's call the cost here C. Let's call toppings T, okay? First, they're telling us about Barrows. So let's make an equation for Barrows. For Barrows, the cost for your large pizza equals $10 plus $1.25 per topping. We just don't know how many of those there are going to be. And then at Brothers, and I don't know if this is true, I really just made these numbers up. Okay, at Brothers, the cost, it says, is $8.75 plus it's $1.50 per topping. Okay, so now let's try to solve and see if we can't understand what is going on in this system. We have $10, oops, I'm going to call this y. Y equals 10 plus 1.25x. I swear. Okay, and then for the second one, y equals 8.75 plus 1.5. What in the blazes? Oh my gosh. I swear I'm hitting the plus sign. Yeah. Let me try my pen. Okay, so there's our system. And look at what's happening. So in red, we've graphed the equation for, oh, it's the reverse of what's on my paper. Here, let me just change that because that's confusing. And make this one red. Okay, so in blue, we have Barrow's Pizza. And look what's happening. We've got a y-intercept at 10, right? That's where the cost starts. And then it goes up by $1.25 per topping all the way across that line. And then in red here, we have Brothers. Starts at $8.75. That's the initial cost for the pizza. And then it's going up by $1.50 per topping until the lines meet right there. Now, what's happening before those meet? Notice the Barrow's Pizza starts out, I'm trying to get this to all fit on the screen here nicely. That's good. Okay, so Barrow's starts out with a higher cost, but their cost per topping is cheaper. And then they intersect, right? And then what's happening? Well, before at the intersection, by the way, let me write this down before I forget. The intersection, the solution, is at 5 and 1620, so sloppy. 1625. Okay, that intersection is where we are the same, where the equations meet, right? It's the solution to the system, but it's more than that. Before that, you can see how the blue is above the red. It means the Barrow's Pizza is more expensive. So it's more expensive to start, and it's more expensive for 1 or 2 or 3 or 4 toppings. But when they get to 5, what's happening is they're exactly the same. That solution means both places are going to charge you $16.25 for the 5-topping pizza. And then after that, the roles reverse. After that, you can see the red is above the blue. After that, it means that Brothers is more expensive, right? If you're going to get 6 or 7 or 8 or any toppings after that, it's going to be more expensive at Brothers. So if you like a lot of toppings, right, you want to go to Barrow's. If you like fewer toppings, then go to Brothers. So this solution was toppings and costs. So this means both places charge $16.25 for 5 toppings on a large pizza. For a large pizza with 5 toppings, but you get the idea. Oops. There we go. Okay? So a little different scenario there. I've got one here for you to try. I think I've given you enough examples. I think you should be equipped with the tools to solve this one. So if you want to give it a shot, then go for it. If not, we can still work this one out together. So it says, at the last school dance, singles tickets were sold for $3, couples tickets were sold for $5. If a total of $537 was collected from 143 tickets, how many couples tickets were sold? So it only asked for couples tickets, but this is like the dimes and nickels. We don't know how many couples or singles tickets were sold. So let's call the couples tickets X. Let's call the singles tickets Y. And if you switch the variables, it doesn't matter. Okay? Well, what we need to do is make 2 equations based on the information that they're giving us. So one thing they tell us is that there's a total of well, it's $3 per couples ticket. It's $3 for singles, $5 for couples, and total of $537 collected. So that $3, that $5, that $537, that's putting all the cost, the money together. So let's make another value equation here, or cost, or money equation, okay? I don't know how you want to categorize that, but it's, we said couples will be X, so it is $5 per couples ticket, plus it's $3 per singles ticket, and they collected a total of $537. So we want to make one equation where we put all the money together. Now the other bit of information they're telling us is that there were 143 tickets sold. So we're going to make another equation for the number of tickets sold. And we don't know how many were couples or how many were singles, but altogether the couples and singles tickets is 143. So now we have our system, and now we can go to Desmos to solve. We're going to have a solution at, let's find out. And zoom back in. 5x plus 3y equals 537. and x plus y equals 143. And big numbers, let's zoom out, and there is our solution at 54,89. And x's were couples. Y's, we said, were singles. And so this question really only asked how many couples tickets were sold. That would be 54. But I'm going to go ahead and put them both, since we have it. If I can spell. And there we go. Okay, so hopefully if you tried that on your own, you were successful. If not, that's okay. These things take practice. Okay. All right, now these were the warm-ups. Some of these on the back, actually the next two aren't bad, but some of them are challenging. They get more challenging as we move on here. So number 4, different type of example. It's an application, not so useful as I think the other two seem to have been. But we're going to try this nonetheless. It says a number is 3 more than another. And if twice the sum of the numbers is 27, what are the numbers? So we have one number, let's call it x, is 3 more than another, let's call it y. These are our two numbers, okay? If we literally translate this first sentence here, a number we called x is our equal sign. 3 more than means 3 plus or plus 3. Another, let's call that y, we said. There's our first equation, okay? Next, it says that twice the sum, that's 2 times a sum, of the numbers. That means we're twice the sum of our x and y is equal sign 27 is our second equation. So this is literally a translating problem, okay? We've got our system now. Let's put it in Desmos and solve it. So x equals 3 plus y, and twice the sum means twice that whole thing has to equal 27, and we solve, and there it is. So we've got a solution at 8.25 and 5.25. Did I put those in? Yes. 5.25, so that's it. Our numbers are 8.25 and 5.25. That probably wouldn't have been too fun to solve by hand. Thankfully, we've got technology to do the heavy lifting. Okay, here's another translation problem. It says the sum of two numbers is 13 and their difference is 23. Find the numbers, let's call them x and y, okay? Unless you like other variables, you can use whatever variables you want. What is the sum of the two numbers going to look like? Well, if I add x and y, that's their sum, that is equals 13. And then it says the difference is 23. That means if I subtract the two numbers, I get 23. So we have an equation for their sum, an equation for their difference. Now that looks pretty easy to solve by hand, but I'm going to go ahead and type it in here anyway. X plus y equals 13. Their sum is 13. Their difference, x minus y, is 23, which makes our numbers 18 and negative 5. So we have a solution at 18 and negative 5. That means our numbers are 18 and negative 5. Not so terrible, if you can translate, okay? Now again, a little bit of warm-up for us. Now we separate the weak from the strong. No, I'm teasing, except a little bit not teasing. These are some challenging problems here. So let's look at number 6. It says Starbucks is making 100 pounds of a new blend of coffee to sell for $4.15. This new blend will be made by mixing two existing blends that sell for $3 per pound and $5 per pound. How many pounds of each should they use? So if you understand what's happening here, they have this mixture that they sell for $3 a pound. They have a little bit of a higher end mixture they sell for $5 per pound. What they're trying to do is mix a little bit of the cheaper one with some of the expensive one to get to something in the middle that sells for $4.15 per pound. Okay? So that's the concept we have going on here. So how many of each should they use? I don't know. So let's say X is the amount of the $3 per pound. So this is pounds of the $3 blend. And then let's call Y pounds of $5 blend. I don't know how much of the $3 blend. I don't know how much of the $5 blend. Those are my two variables, okay? So now we need to make two equations. One equation comes from this. The new mixture is going to have 100 pounds. So the number of pounds, one equation, X amount of the $3 blend plus Y amount of the $5 blend has to make 100 pounds altogether. And now my second equation has to come from the money. We've got $4.15 per pound, $3 per pound, $5 per pound. So all that money stuff has to go together. So let's put the value in here. Okay, our value equation. The $3 blend is $3 per pound. So 3 times X, $3 per X amount of pounds, right? Plus the $5 blend is $5 per pound. So it's $5 per pound of Y. So 5 times the Y. Now that's going to combine to get this $4.15 per pound blend. So the $4.15 per pound has to go here, but it's per pound, right? So notice the 3 got multiplied by the X that was here, the 5 gets multiplied by the Y that's here, and the $4.15 has to be multiplied by the 100 that's here. So it's 3 per X, 5 per Y, and it's $4.15 per 100 pounds of the mixture. And that is the tricky part with this one, okay? So we're going to put this in Desmos now to do the hard part. So it's going to be X amount of pounds plus Y amount of pounds to make 100 pounds total. It's $3 per pound of that plus $5 per pound of that, equaling $4.15 per pound of the mixture. And that tells us we are 42.5, 57.5, and that is exactly how many pounds of each we need to use. So we're going to do 42.5 pounds of $3 blend and 57.5 pounds of the $5 blend. So if we were to mix 42.5 pounds of the $3 blend with 57.5 pounds of the $5 blend, we will get 100 pounds of a blend that we can sell, that Starbucks can sell for $4.15 per pound without losing any money. Okay? That was a tough one. We're going to do another one like that, but instead of a fun Starbucks problem, we have a metallurgist problem. So a metallurgist is someone who works with metals. This metallurgist needs to make 15 milligrams of an alloy that contains 65% iron. He's going to melt and combine one metal that has 5% iron with another one that has 80% iron. How much of each should he use? This is just like the Starbucks problem, right? He's got a 5% iron, he's got an 80% iron, and he needs to mix the two to end up with a 65% iron. So one's not enough, this is too much, he's got to mix to make his blend, okay? So let's see. It says how many of each of these metal mixtures is he going to have to use? So let's say X is the milligrams of 5% iron, and we're going to have Y milligrams of the 80% iron. Alright, so one equation, just like before, is going to be for the total number of milligrams. Number of milligrams. There's going to be X milligrams of 5% iron plus Y milligrams of 80% iron, and 15 milligrams total. And the other equation, again, just like the Starbucks problem, is going to have to put all the percents together. I swear I said green. The 65%, the 5%, the 80%. So let's put the percents together. The percent per milligram. all those together. So the X is 5%. So it's 5% per milligram here. And if you want to make that a decimal, you can. You can make them decimals all the way across, or you can use just the numbers all the way across. Either way, as long as you're consistent. So 5% per milligram there. Plus, it's 80% per milligram of Y. And then it's going to be 65% per milligram of the mixture, which is 15 milligrams. So just like in the last one, where we take our percent and multiply by the number of milligrams, take our percent, multiply by the number of milligrams, take our percent, multiply by the number of milligrams. Gotta have that piece in there to get an answer that's going to make sense for us. So now, the easy part, right? Now we go to Desmos. So x plus y equals 15, cheated a little on that. 5x and 3y is going to equal 65 times 15 for the second one. And our solution, what did I do? This is no good. I should not have a negative value in here. What did I do? Did I type something in wrong? Oh yeah, sure did. I'm like, you guys are probably seeing this. But you see, this happens, right? We all make mistakes here. Maybe you don't, but I definitely make mistakes. I ended up with this negative solution, so I knew I did something wrong. Well, I typed the second equation, and I have a 3 there, where I need to have an 80. And that should give me something in quadrant 1. And there it is, tiny as it is. There it is. So 312 is our solution. And remember, this is x and this is y. So this tells us we need 3 milligrams of the 5% iron mixed with 12 milligrams of the 80% iron. And mixing those two together will produce 15 milligrams of an iron, or of a metal that has 65% iron. Okay? Complicated, I know. But I think if you're getting the concept, this would be a good opportunity for you to try. So feel free to pause the video and give this a shot. Otherwise, again, let's do this together. So Eugene, he wants to make 13.8 ounces of a 35% alcohol solution by mixing a 50% alcohol solution and a 20% alcohol solution. How much of each should he use? So X, let's call that the ounces of... he's trying to mix 20% with 50% to get to his 35% mixture. So don't know how much of each of those that he's going to mix together. So let's say X is the number of ounces of the 20% solution. And let's say Y is ounces of the 50% solution. So we know he's going to make 13.8 ounces altogether. So one equation for the number of ounces. X amount of that, Y amount of that, 13.8 total. Okay, just like before. And then a second equation where we put all the percents together. So we're going to put the percent per ounce. Okay, percent per ounce here. So it's 20% per ounce of the X. It's 50% per ounce of Y. And then the mixture is going to be a 35% per ounce. So 35% per 13.8 ounces there. And now we're ready to go to Desmos. So x plus y is going to equal 13.8, and then 20x and 50y equals 35 times 13.8, and our solution right there is going to be 6.9 ounces of each. 6.9 and 6.9. And again, this was x and this was y. So it's going to be 6.9 ounces of each. And that one should make a little bit more sense, that it's the same amount, because if you think about 20 and 50 and 35. There's exactly 15 units away there and exactly 15 away there. So since the number we're looking for is right smack in the middle, it should make sense that we have an equal number of each of those to mix together. Now that I pointed it out, at least it should make sense, okay? So I think you have enough to go on for your practice here. This will be a challenging one. Just do your best and reach out if you need some extra help. All right? Take care.